Hi everyone, welcome to week number 8 of the problem solving session for the course selected topics in algorithms. Okay, my name is Bhavedeep Rai and I am a PhD scholar from IIT Madras, and these solving sessions will be happening every Tuesday 6 p.m. to 8 p.m. where we'll be taking a few problem related to the course, and we'll be solving them. And if you have any questions or any doubts, then we'll be discussing them. We'll also be discussing some of the assignment questions that are in the course. Okay. So the original session, I had a technical issue with that. So I'm doing a re-recording. But anyway, the technical session was more concept based, in a sense that I was doing a very deep recap onto the topic. So I did not get to cover a lot of actual problems. So this time I wish to overlook, in a certain sense, the concepts, as in I'll only be going through them briefly, very briefly, and then I'll move on directly to the assignment questions, and then to some other questions related to this week's topic. Okay, so I'll move on from this. Okay, so what is this week's topic? NP-complete problems, weak NP-completeness, and self-reducibility. Okay, so let's have a quick recap. Okay, decision problems. Okay, what are decision problems? They are just problems where the answer is either yes or no. Okay, there could be other types of problems. This is just one type of problem, and this is what we primarily focus on. An example of a decision problem is, given a graph, is there a cycle in it? Okay, is there a cycle in the given graph? The answer is yes or no, hence it's a decision problem. Now, search problems. Search problem is when you are actually looking for the object. Okay, you are looking for an object. Problems where an example needs to be found which satisfies your given constraint. Okay, for example, locate a cycle in the given graph. So, of course, if it exists, if it does not exist at all, then probably return invalid or something like that. But as long as there is a cycle in the given graph, then you are supposed to return a cycle. What do you mean by return a cycle? Maybe you specify the vertices or you specify the edges, and that will be your answer output of the algorithm. Now, optimization problem. Well, optimization problem is also a type of search problem, except you are trying to you have what is called an objective function, which you are trying to either maximize or minimize. Say finding the minimum path is an example. Finding the maximum length path is an example in a graph. Okay, and finding the maximum value in a knapsack problem, that is an optimization problem, and so on. So an example is locate the largest cycle in the graph. Okay, and previously it was just locate the cycle. Now we want the largest cycle. Okay, so one thing we can immediately observe is that search is a much more difficult problem than decision. I wouldn't say much more difficult. It's at least as difficult as decision. Okay, that's a better way to say it, right? So why? Because given a search problem, let's say you have an algorithm to a search problem, you can always form a decision problem. For example, search problem is locating whether there's a cycle in the graph or not, and let's say you locate it, right? And let's say that algorithm is very simple. Now, the question about whether there is a graph or not, as long as you give a non-zero answer, okay, I am good with it. So the search problem, I mean, if search problem is easily solvable, then decision problem is also by that fashion easily solvable. But however, the other sense that if you have a decision problem, okay, then doing the reverse. Okay, if you have a decision problem, do you have a cycle or not? Yes or no? Let's say yes. Now locate the cycle. Is that very easy to do? Does not seem to be very easy to do. Just given the answer that it is yes or no, you need to do something non-trivial to do that, probably. Hence, search problem, it seems to be more difficult than decision problems. Anyway, major part of this course will be this week will be based on decision problems. Okay, so talking about decision problems, we want to classify problems further in terms of ease of solving them. Okay, so we have one such classification, that is P and NP. There could be other what are called complexity classes. Okay, but we are majorly focused on P and NP. P are those decision problems that have a deterministic polynomial time algorithm based on the input. For example, two-sat, bipartiteness, cycle, maximum flow, maximum cut, and so on. So, for example, earlier in the course, maximum flow, we had seen an polynomial time algorithm for that, which is the Edmonds-Karp algorithm. And max cut, we could derive polynomial time deterministic algorithm from the maximum flow algorithm itself. Okay. What is NP? Well, these are decision problems where solutions are easy to verify. Okay. Now, what do you mean by that? Here's the formal definition. A language or equivalently a problem is in NP, then for every input, okay, possible, if X an input, if the input belongs to L, which means it is the yes instance of the problem. Okay, the problem says yes there. Then there will always exist a Y, which we shall call a certificate. Which is of polynomial size. Okay, certificate, and not only that. Oh, now, what does the certificate do? Well, there is a deterministic polynomial time algorithm which we shall call V. Okay, V stands for verifier. Okay, and the verifier, given the input X and the certificate Y, will always say yes. Look at the fact that it says if and only if. What does if and only if mean? It means that if X does not belong to this, so that is if X does not belong to the language, you can equivalent say, okay, if and only if Vxy says no. Okay, equivalently, the verifier says no. So, but this does not immediately give us a polynomial time algorithm, because who will give us the certificate? Well, algorithm is guaranteed if it is an NP, but who will give us the certificate? That is a problem. One solution is to go across all possible Ys and then check whether it's a certificate or not. If it's a certificate, then it will say yes, and therefore you will say X is in the language. X, the problem will say yes for that particular input X. Right? But how much time will it take to go across each certificate? Well, there are polynomially size certificates, and so it will be 2 to the polynomial, which will be exponential. So you immediately see that making this NP problem deterministic, okay, deterministic, will pertain some difficulty, because the trivial way to do it will take exponential time. So now I just want to go over some examples about checking whether a problem is in NP or not. Okay, for example, here is a problem which is called cycle. Okay, cycle is input is a given graph. Okay, it may be directed, undirected. Now let's say directed. Okay, let's say directed. Okay, so given a directed input graph, you want to output yes if there is a cycle, no otherwise. So how do you do that? So, okay, finding an algorithm for it is something else, but I want to just prove that it's an end. Finding an algorithm, let's say I want to find whether there is a cycle or not, and let's say the graph is okay, it may not be connected. So what is the idea? Well, I'll just pick a vertex, okay, and then do a DFS, okay, and if it so happens that I'm starting a process, okay, and without backtracking, I did DFS, and then without backtracking, I reached the same vertex itself. I got a cycle. The algorithm is even simpler if the graph is connected, because if it is connected and it does not have a cycle, then it necessarily has fewer edges. It has less than n minus 1 edges. If it has more than n plus 1 more than n minus 1 edges, then and it is connected, then it definitely has a cycle. Okay. So, but what I don't want, that shows that it is in P. How do I show that it's in NP? Well, if I give you this graph and then I ask you whether this has a cycle or not, and then your answer is yes, and I tell you that I'm not convinced, convince me. So what would be the natural way that you would convince me that there is a cycle in the graph? You'll just simply point out the cycle to me, right? Or you'll just give me the vertices, right? For example, 5, 3, 6. So you'll tell me that, oh, okay, look here, 5, okay, sorry, 5 to 3, 3 to 6, and 6 to 5. Okay, look here, this forms a cycle. Then I will check that adjacency matrix, and then I'll say, yeah, this is true. This is a cycle. Okay, so 536 is actually a certificate, valid certificate for this instance of the cycle problem. Okay, now why is this a valid certificate? Well, the number of, there are only v many vertices, okay, capital V, and size of v many vertices, and the total size of the graph is like v square, because adjacency matrix. So this of course will be smaller than v, and therefore it will be smaller than v square, which means that it's smaller than n, which is the size of the input, and which means it is polynomial size of the input. So, but what is a verifier algorithm? Well, verifier algorithm, I've written it as DFS given the graph and 536, but do you need to do a DFS? If you give it as a sequence, okay, if you give it in the correct sequence, I don't even need to do a DFS, right? So, yeah, okay. Now, another question is bipartite. So, what is a bipartite graph? It is a graph where you can actually partition the vertex set into two parts, A and B, such that any edge, okay, between U and V will always have that U and V will always belong to A, U will always belong to A, and V will belong to B, or vice versa. Okay, but it can never be that there is an edge between two vertices in the same partition in the bipartite. Getting it? So, and how do you verify whether it's a bipartite graph or not? Okay. Okay. So how do you verify whether it's a bipartite graph or not? I'm not asking you to check bipartiteness. I'm telling you, given a graph, give me a small certificate. Let's say it's bipartite. Give me a small size certificate which will actually prove that this is bipartite. And that can be done as follows. You give me the partition. You tell me the set A is this, the set B is this, and we are done. And of course, it's the size of that particular certificate is smaller than the graph, right? So, okay, that is another thing. Now click. So what does this mean? Bipartite is an NP. Okay. Now click. What is a click? It's a small complete subgraph, which means take any points. Okay. And so what is a click? Sorry, a click is a subgraph. For example, 276, and if you look here, then they have edges across for among each other, all of them. Okay. For example, what I mean is 2 is connected to 7, 6 is connected to 7, 6 is connected to. So 2 is connected to both the others, 7 is connected to both the others, and 6 is connected to both the others. This is what is called actually a complete graph, right? I think I have written, yeah. So these are called complete graphs, right? They have edges. Each of the vertices, each pair of vertices are adjacent to one another, and so on. So now we are asking, given a graph, you want to check whether, okay, here's the problem, given an undirected graph, okay, and a k is at least 0, k is an integer, okay. Now you want to ask if there is a click of size at least k. Now if I ask you whether in this graph if there is a click of size 3, you will say yes, and I'll ask you how, you'll just tell me that okay, 267. And then if I ask 4, okay, is there a click of size 4? That is G4. And then you'll say yes, you'll say 2367. I'll verify it. How will I verify? I'll just go across each vertex and check whether their ones in the adjacency matrix correspond to 276. Okay, and then I ask you 5, then you will not be able to tell me because there is no click here of size. So this is an important point about NP problems. Okay, that if the certificate does not exist, if the answer is no, you will not be able to find the certificate at all. Okay, you will not be able to find the certificate at all. Now that is what is called an NP characterization of the problem. Okay, so for example, here, let's say you try to fool me. I ask you, is there a click of size 5? You tell me yes, let's say, even though there is no. Now I tell you, okay, show me, and we agree that okay, to a certificate would mean that you need to show a click to me in this context. Let's say my verifier algorithm does that. You will not be able to produce a subgraph which has 5, uh, which is K5, complete graph on 5 vertices. You cannot do that. You will not be able to find it. Hence, you cannot fool me. Hence, the model of NP completeness is robust that way. Okay, so this also shows that click is an NP. And finally, this question, composite. Okay, input is a number n in binary. Okay, and your output is yes if n is not prime, no otherwise. Okay, so what would be a natural way to convince me that something is composite? For example, I have 12 given here. I have 12 here. How do you convince me that it's composite? So what you'll do is you can say that this is not uh, this is composed of several other numbers. That is, just give me the prime factorization of this, or just give me any factorization of this. And what I'll do is I'll just verify if this factorization is valid. That is, I'll multiply them, and then I'll get 12. And if it is not composite, then no matter what factorization you give me, you will not be able to give 7. Considering the fact that the factorization does not contain the number itself and 1. Otherwise, even primes would be accepted, right? So here, certificate is the prime factorization. Okay. So okay, next thing is reductions. So I'll not get into it in depth from a conceptual perspective, but reduction is a way to convert one problem to another. So we'll be focused more on what are called carp reduction or many one reductions. A reduces to B, polynomial time many reduces to B, and this is many one is also called carp reduces to B. Then for all inputs X, if there is a reduction from from a string to another string such that x is in A if and only if sigma x is in B. So this is where the transformation happens. So if x is in A, then sigma x is in B. So what does if and only if mean? It means that if x is not in A, then sigma x is not in B. Okay. So for example, so this we don't need, this also we don't need. Okay. So here we have it. So I'll shift it. Reduction. Okay. So what it means is, if I want to build an algorithm that solves a problem A, then what I can do is I can take an algorithm that solves B, I can transform the problem, and if B says yes, then A will say yes, and B says no, then A will say no. Okay. So here's what we have. A clique is a subgraph. We already know what a clique is. Okay. Now, what is an independent set? So a subset of vertices is said to be independent if no matter what pair of vertices I choose, no matter what uv I choose from S, u comma v will never be an edge. Now, so we know the clique problem. Independent set is just the following problem. He'll say yes. Input is a graph G. Output says yes if there is an independent set in G of size K, versus K and K is 0, no otherwise. So that's the independent set problem. So now we want to show that clique reduces to independent set in polynomial time. So what does that mean? Given an algorithm for independent set, I should be able to solve clique. Right? Given an algorithm for independent set, I'll be able to solve clique. So how do I make use of the algorithm for independent set? So it should use the independent set algorithm as a subroutine. So in set solver. So for example, assume an efficient. Okay, no need for efficient. Okay, an independent solver exists. We need to use this as a subroutine. So, for example, in this particular graph, okay, in this particular graph, so I'll remove this to make it less complicated. So here you observe that there is a K4 setting inside. So there's a clique of size 4. I want to, for example, detect whether K4 is there or not. But I want to use the independent set algorithm. So what do I want you to observe? Observe that independent set is actually the opposite of clique in a philosophical sense. What does clique say? A set of vertices where all of them are connected. What does independent set say? A set of vertices where none of them are connected. So you see that clique is just a lot of edges. Maximum number of edges, and independent set is no edges. So the idea is that if this is G, I will transform it into the graph G bar, which means G complement. What is meant by complement? What is meant by complement is that if there is an edge, I'll remove that edge. If there is no edge, then I'll put the edge. Okay. So G bar can be 1, 2, 3, 4, 5, 6, 7. Okay. Now we can proceed to add edges. So 1 is connected to 3. Okay, so to make it less complicated, let's say the graph originally is also connected to 4. Let's say 3 was connected to 6, and yeah, okay. So 1 is connected to that way 5, 3, 6, and 3 is connected to 2. Sorry, 3 will be connected to 1, 7, right? 3 is connected to 1, 3 is connected to 7. Okay, and 7 is connected to 3, 7 is connected to 1. Okay, that we forgot to do, and 7 is connected to 6. So you should observe something that, see, 2, 3, 4, 5, which was the set of vertices in the previous click of K4. Look at those same vertices. It cannot be that there is an edge between 2, 3, 4, 5 among them. Why? Because we are taking the complement of the graph, which means if there is an edge, then you should remove them. So if there is since a K4 is, I mean, in this 2, 3, 4, 5, all of them are connected to each other. In the complement graph, none of them will be connected to each other. In other words, what is this? This is an independent set. So this is an independent set. So if you have an efficient, so what does it mean? Not only efficient. So if you have a if you want to construct an algorithm that solves click then you can construct it by actually using an independent set sort. By actually doing a reduction. And what is this reduction? This reduction is exactly G bar. And what is X? X is G. And this should be doable in polynomial time. For it to be a carb reduction. This should be doable in polynomial time. And is it doable in polynomial time? Yeah, because how do you complement the graph given the adjacency matrix? You just flip all the ones to 0, zeros to 1. So flip all zeros to ones, ones to zeros in the adjacency matrix. Okay, and yeah, by the way, if it said yes, oh, okay, sigma x key, by the way, which is gk sigma g k. If it says yes, then output yes. If it says no, then output. And that's okay. So now that we have that, uh, we'll start with the assignment questions for the previous week. Okay. Question says, which of the following problems are known to belong to the complexity class NP? Oh, by the way, so I had should be having a note here somewhere. Okay, it's not here. So it's where the what? Okay, I don't have it here, but so here's the diagram. So this is okay, they are not equal in size. So this is NP. Well, NP contains P. Okay, and this is NP intersection coNP, and this is coNP. Okay, and this is the set of all problems, all languages, which is the power set of sigma star. So this is what we have now. We don't know whether P is equal to. So firstly, we know P is contained in NP. We don't know whether P is equal to NP or not. Not known. I mean, this is one of the biggest problems until now, and it has not been resolved, and probably will not be resolved anytime soon. So, what is coNP, by the way? coNP, in whichever problems you NP had said no, say yes. In whichever problems NP had said yes, say no. So that is coNP. Okay, and what about NP versus coNP? We do not know. Open question. And what about this NP intersection coNP? It contains P, because P, when you complement it, you still get P. So now NP intersection coNP, does it contains P, but does it strictly contain P, or is it equal to P? Don't know. So these are some of the very open questions which are not resolved until now. And now we have something called NP completeness. First, NP hardness. NP hard means if every problem in NP reduces to that problem. For all L in NP, okay, L reduces to that problem A. Okay, then A is NP hard. Now NP complete means you sort of represent that particular candidate for all. So first thing is that you belong to NP and A is also NP hard. So hardness as well as completeness. So it should also be NP hard. It should also belong to NP. Okay. So if these things are satisfied, then it is NP. Now you have examples, something like sat, 3sat, click, and therefore independent set and so on. Okay, we can't cover it in detail right now because it's a vast topic, but we'll see as it goes. Okay. Now, which of the following problems are known to belong to the complexity class NP? So, Boolean satisfiability, it is NP complete. What is SAT? Not only is it in NP, but it's in NP complete. So, what is SAT? Input is a formula phi which takes n inputs, and output is yes if phi is satisfiable. No otherwise. No if there is no input setting which will actually satisfy the formula. Okay. And Boolean unsatisfiability. So this is satisfiable. Why? Because I can I can always give you a satisfying segment as my certificate. If it is satisfiable, then I'll give you those settings of zeros and ones to the input for which this formula is satisfied. So this is an NP. In fact, NP complete. Now this is an important thing. Why? Because now the next part, Boolean unsatisfiability, unsat, is just the complement of sat. It's just not sat complement. It is the complement of sat's answers. Okay. So it says all those phi says that phi is unsatisfied. Right. So that is unsat. So now if so, what does that mean? This means that unsat is in coNP, and if unsat is also in NP, then its complement is also in NP, and then you show that NP is equal to coNP intersection NP. Remember the diagram. Unsat is in NP, right? Unsat is in unsat is in NP. I mean, if this is an assumption, okay. If unsat, we already know that sat is in NP, okay, which is NP complete, and you are saying unsat is also in NP. So what does that mean? Sat lies somewhere here, that way, by assumption. Sat lies here, but since everything reduces to it, it means that NP will collapse to this region, NP intersection, and hence coNP will also collapse to this region, because complement of every NP language is an NP intersection coNP, then it means complement of every coNP language is also an NP intersection coNP, and which implies that P equals NP. Let's show this. So not no. So unsat cannot be an NP. Okay, the remaining shortest path in a graph, longest path in a graph, is just shortest path is given graph G and K, is there a path of length at most K, and longest path is GK, is there a path of length at least k. Okay, or okay, sorry, I think it's the opposite. At least k, at most k. So which is simpler? Well, longest path problem can always be solved. No, just to give, um, just check if edge is there or not. Check if single edge even exists. Even if a single edge exists, then there's a path of length 1, which is at most length k, because k is at least 1. So this is trivially doable. Shortest path is a difficult problem, but is it an NP? Yes, it is an NP. I mean, this longest path we showed that it can be done in polynomial time, so it's in P, therefore it's an NP. But of course, longest path also you can always give an example. That is, this is your certificate, always. Now, what about shortest path? Well, you can always give certificate. Can always be given. So both of them are in NP. So sorry, B should not be there. Boolean unsatisfiable cannot. Okay. So that is done. Now, which of the problems are known to belong to the complexity class coNP? Well, Boolean unsatisfiability. Longest path also. Why? Because longest path is in P, we said. Is in P. So shortest path in a graph, it cannot already belong to coNP because shortest path is actually NP complete. I'll tell you why. Because shortest path actually is NP complete. Okay. Now, why is it NP complete? The Hamiltonian path problem, which is already NP complete, reduces in polynomial time to shortest path. How? Well, to check whether G has a Hamiltonian path or not, what does Hamiltonian path mean? It visits all the vertices. A single path which visits all the vertices is same as saying whether there is a path of length n. G comma the number of vertices as your k. And you're done. So another question: which of the following are correct? The vertex cover problem, polynomial time reduces to click problem. Click problem, polynomial time reduces to vertex cover problem, to sat problem, and so on. Okay. So here are the main facts. Okay. It's done in the lectures that vertex cover, click, vertex cover, click, and okay, only two are NP complete. Next, to sat is in P. It's done in the lectures, and okay, right. So this, what does vertex cover, click, NP complete mean? Anything that is in NP will actually reduce to VC and click. For all L in NP, L reduces to vertex cover as well as click. Right. So which means that 2sat will also reduce. So it means that VC reduces to, since it itself belongs to NP, VC reduces to click, and click also belongs to NP. So click also reduces to VC, and 2sat also reduces to VC as well as click. But will VC or click reduce to 2SAT? No, this cannot happen. Because 2SAT is in P. If 2SAT is in P and an NP-complete problem reduces to it, it means you can solve vertex cover, click, and so on in polynomial time, and therefore P is unless P is equal to NP. And this is not known. Okay. So 2SAT click problem, so D cannot be true. Okay. Which of the following problems are NP? We already saw this, right? Okay. Longest path, shortest path, done. Okay. So longest path. Okay, wait. Shortest path is which one? Shortest path is NP complete. Done. Shortest path is NP complete. Longest path is very trivial. It is in P, so it cannot be NP complete. Longest cycle in a graph. Longest cycle in a graph. This is interesting. Can you reduce? Can you? Okay, first of all, can you solve it in polynomial time? Well, to solve it in polynomial time, it is not very clear. There is no counting argument. If I do a DFS, also it may be difficult. But here's one way you can actually reduce the Hamiltonian cycle problem to the longest cycle problem, right? Because whether a graph has a Hamiltonian cycle or not is same as saying whether the graph has a cycle of length at least n or not. Oh, okay, so longest cycle. So I have mixed up the two, it seems. So this should be no, this, sorry, I mixed up the definition of the two. That's why, okay, this is fine. So it should be B, C. Okay. This should be longest. I mixed up the definition. So this should be interchanged. This should be longest. Shortest. Okay. So longest cycle in a graph is therefore NP complete. Because this is NP complete. Okay. Finally, maximum matching in a graph. Can it be so? So this is C. Maximum matching. This cannot be true. Because we already saw. Okay. So this is not bipartite, right? Okay, this is not bipartite. Does maximum matching? I feel like this is not true. This is true. Maximum matching. Let me just confirm once. I believe there are only randomized algorithms for this. Okay, yeah, there was an algorithm which we were dealing with, right? Okay. So bipartite case was also done. The Hopcroft algorithm would be the one which is, so since it's already in P, it will not be. So in one of the previous lectures, it was during the matchings part of the week. I think it was in the third week or fourth week was when this was done. Okay. So that is NP. Okay. Okay. Which of the following problems are NP hard? Boolean satisfiability, maximum click, in bipartite graphs, halting problem to SAT. Now, Boolean satisfiability we already know. Maximum click in bipartite graphs. Maximum click in bipartite graphs. So you want to check whether there is a bipartite click out, right? And um this should be doable using flows. That's what I think. Yeah, this one I'll confirm next week once. Halting problem. Well, halting problem is way hard. It's all the way to um, um, outside NPP, everything. Okay, because okay, I'll give a simple exposition. Halting problem is given input as algorithm and its input. Question is does okay, and A, let's say A halt. This is undecidable. You cannot come up with an algorithm that does this. Okay, and this everything Boolean satisfiability and whatever this all comes inside um, the decidables. So undecidable language would be much more powerful. Okay, so so here's another question. We saw that in the course the 3 coloring is NP complete. Okay, you can reduce 3 sat and so on to it. Which of the following is known? 2 coloring is in P. 2 coloring is in P or not? So this is yes. Why? Because 2 coloring is same as bipartite. Okay, 2 coloring is same as bipartite. So that is G is bipartite if and only if G can be 2 colored. Okay, and check it out for yourself. Okay, I will not prove it here, but now to check whether the graph is 2 colorable, I want to check whether it's bipartite or not. Checking whether bipartite or not is very straight. So idea is you pick a vertex, color it green, the ones adjacent to it, color it red, then the one adjacent to the red one, color it green, then the one adjacent to green should all be colored red. Now here this green and this green is adjacent to this red, so I'm coloring it red, and this red is adjacent to this green, so I'm coloring it red, right? Now I have a contradiction. So this is not bipartite. So that is the algorithm to do it. You pick a vertex, color it, check whether the neighbors are colored, whether it's the same color or not. If not, then keep coloring it. And so 2 coloring is NP. 2 coloring is NP complete. Again, that cannot happen. 2 coloring is in P. If 2 coloring is NP complete, then all hell breaks loose. P is equal to NP. 4 coloring is in P. Okay, 4 coloring is in P. This cannot happen. Why? Because 4 coloring, so because 3 coloring itself reduces to 4 coloring. And if um, 3 coloring is NP complete, then whatever it reduces to will always be NP complete. Okay. Why is 3 coloring uh, reduced to 4 coloring? Well, if you want to check whether uh, uh, a graph can be 4 colored or not, one moment. Okay, okay. Sorry. This is in P, surprisingly. Okay. Um, you are asking whether a graph can be 4 colored or not, and this problem is the statement of the 4 color theorem, which was very recently proved. And it says that any graph can actually be colored with 4 colors. Uh, but that would be for planar graphs. Okay. But that is for planar graphs. Okay. So there should be a reduction from 3 coloring to 4 coloring. That is what I am thinking. But it does not immediately strike me why there should be a reduction. But yeah, okay. There is another way to do it. 3 coloring will reduce to 3 sat. Now, 3 sat itself reduces to 4 sat, and 4 sat reduces to 4 coloring by the similar coloring argument that 3 sat reduces to 3 coloring reduces 3 sat. So this is one way to show it. Whether a direct way exists or not, that I need to check. I'll confirm it next week. Okay. So 4 coloring is NP complete, and therefore similar logic for coloring is P cannot have. Okay. Uh, Now self reducibility in SAT. What is self reducibility? You can solve the problem with smaller instances of the same problem. For example, you have an input phi and x1 to x2 so on till xn, and what you do is you fix. Here is an algorithm to let's say you are uh, let's say I allow you uh, to check whether it is satisfiable or not. Is it possible for you to find an input that satisfies it? So we are doing the opposite. So we, given the um, uh, problem, given that you can solve the problem easily, can you find the certificate? That's another way to say it. So what we'll do is we'll systematically and sequentially start assigning, fixing the inputs. Okay. So phi of 0 x2 and so on till xn, and phi of 1 x2 till xn, then phi of 0 0 x3 to xn, then phi of 0 1 x3 to xn, and phi of 1 comma 0. So every left means a 0, 3 comma xn, and phi of 1 1 x3 xn. And so you have this, and you have this, but what you are doing is actually is you check whether phi is satisfiable. Say answer is yes. If no, then you cannot find any satisfying assignment anyway. Now what you do is you've gone here, now here you check. If yes, then you go down. Now here again you check. I mean, if if this path said yes, then no need to check here. Similarly, this guy said yes, then no need to check here, because some guy in this subtree will definitely satisfy. So I just need one satisfying assignment, right? So I'll finally reach a bottom, and the leaf will be the satisfying assignment. And now what do you have? The algorithm. What is the running time of the algorithm? The running time of the algorithm is the depth of the tree. And okay. And running time is the depth of the tree. And what is the depth of the tree? It's log n, where n is the number of inputs. Okay. So okay, that is called the self-reducibility. So what does self-reducibility imply? A polynomial time algorithm to solve SAT also means we can find the satisfying assignment in polynomial time. This is true. You saw from here that depth of the tree is log n, which is the number of satisfying assignment. It just takes that much amount of time to actually find the satisfying assignment. But not just log n, it will be the log the number of the leaves. Sorry. It will be sorry. The depth of the tree will be the number of inputs you're fixing. If you reach the bottom, it means you fixed all the n inputs. Is n, so which is polynomial. Okay, and any NP complete is self-reducible. Now this is interesting. This is actually true. Why is it true? Because if I have if I have any problem, let's say I have click, I'll transform it into a circuit. How? Using the reduction, because click is also in NP. Click or any other NP problem can be transformed into Xn. Then what will I do? I have this yeah, right. So I have this x1 to xn. Now I have two sets of. Now what can I do? I can transform this back into a click problem, and according to the answer I can decide to split, and so on. So the idea is same. Okay, so the idea is same by using the reduction. If any NP complete problem is in polynomial time algorithm, then yeah. So by A and B, it follows that for any NP complete problem, if there is a polynomial time algorithm, then there is a search version polynomial time algorithm. Okay, and okay, so here's another problem. So far we've only been talking about 3 SAT, say, and CNF SAT. So what is CNF? It is conjunctive normal form, which means the formulas are of this form. This is a CNF. You have a conjunction that is an AND on top, and you have disjunctions on bottom. And DNF. What is a DNF? Well, it's the opposite. You have disjunction on top, and you have conjunctions on bottom. Okay. Now, why are we only interested in CNF SAT? That is the question. Why not DNF SAT? Well, it so happens that DNF SAT can be done in polynomial time, and that too rather easily. Okay. Why? Because let's say you are given a DNF. Okay. And now, what you need to do is you need to check whether this DNF is satisfied. In order to satisfy this OR, okay, in order to satisfy the OR on top, it is enough to satisfy any of the ANDs below. Wait, I can either satisfy this or satisfy this because of the property of OR. Now, given AND of say x1 and x2 bar and x3 and x4 bar, then this term can always be satisfied by setting x1 is 1, x2 is 1, x2 is 0, x3 is 1, where basically wherever you see a negation you make it 0, x4 is 0, and once you do that this entire term will become, and so the algorithm is so simple, and therefore your answer will be therefore your answer will be always satisfiable unless, okay, so when can you not do something like this? Okay, so here's the bad case, is when you have x1 and x2 bar and x2 and say x3. So here you will assign 1 1, here you will assign 0, here you should be assigning 1, right? But how can x2 be 0 and 1 at the same time? So this clause cannot be satisfied. This is the only case when you cannot do it. So basically the algorithm is go across all AND terms, check if there exists a term, this is an AND, okay, logical AND, a term where some xi bar does not exist, and if you find it, then it's done, over. If you find such a term, then you can always find a setting where the DNF is satisfied. This is why DNF SAT is not looked into, whereas CNF SAT now becomes a much more difficult problem, because see, to satisfy this AND clause itself, you need to satisfy all of these. Now, if you need to satisfy, let's say, this OR and this OR at the same time, if I put an input setting that satisfies this OR, let's say, then because of that input setting, maybe this guy is unsatisfied, and if I again try to satisfy this guy, and maybe this guy is not satisfied anymore. So CNF SAT itself becomes such a tough job to do. Okay, but it so happens that if you have 2 CNF, then you can do it. But as soon as you notch up the version to 3 SAT, it becomes NP-complete. So this is another interesting thing. So the next question, I won't really solve it, because this, I just want you to be aware of it. Okay, so this concept of weakly NP-complete. Okay, the knapsack problem subset some problem are what are called weakly NP-complete. So which means that they are NP-complete but have pseudo polynomial time algorithms. So outline these algorithms. So look into it. So you can, these are very popular algorithms. You may already have seen it. So you see the knapsack algorithm, the DP knapsack algorithm. Which uses dynamic programming, and then the subset sum problem, is it also DP? Not really DP actually. It's actually what are called a state search problem, state search algorithm. So so this is not directly complexity based, so that I'm not getting into it. But check it out once. If you cannot um, uh, understand it, then please let me know. Okay, I'll explain it to you. Um, okay, so with that, we come to the end of this session. So we'll meet next Tuesday, okay, at 6 p.m. again. Okay, then. Thank you.